Hi everyone. Welcome to the lecture. One of my stock of AI, I think this one was sent to me by a student, memes that I found in the last while. Please attend the pre-prac lecture after this, very important. The third prac is the sort of major one of the semester. It's also the one people normally struggle with the most. So please go. David was AL last year, and based on a lot of the things he saw, he's actually added extra things to the pracs and improved the explanations. Go listen to him. It'll be well worth your trouble to do so. Then also, I think it was, where's he now? You who told me there was a problem with an old tests memorandum. If you do encounter something like that, or you find an answer you're not sure of, let me know. I do make mistakes, it does happen, and it was 2017's first semester test. That was probably the first test I set in this course, ever. But there was a mistake in the depth first search memorandum. So it does happen. If you do find something like that, please let me know. If you look on the cover page of my test, you'll see one of the things that I've included recently is a version history. So that you can actually see when I make mistakes, I gradually correct them over time. So you can actually see I do this. So if you do find something that you're not sure about or that you think the memo is wrong, please let me know. I will gladly correct it, because the stuff's supposed to help you, not to cause additional problems. All right, anything from your side at this stage? Okay, good. Right, dodged the bullet there. All right, at least this isn't like when I used to teach EIR, because the problem was there, you'd have a bunch of mechanical engineering students. So they wouldn't talk to me because I'm not one of their lecturers. But then they'd have class rep meetings, which would then be reported to their HOD, which would then come to our HOD, and it would then come down to me. And in corporate structures, anything that comes down tends to accumulate a fair amount of brown stuff along the way. So, just tell me! So yes. But anyway, I guess the point I'm trying to make is if there is anything, please let me know, and I will do my best to correct it. All right. So yesterday we started looking at this example of an alpha-beta search. Oh, one of the questions I was asked after the lecture yesterday was, please, can we have access to the memorandum? You've got it. It's already available. That's why I always try to tell you where the test or where the question comes from that I'm working from, because then you can actually hop on ClickUp and download the memorandum with the worked solution. So this is from last year's semester test 1, and that exact sheet is a straight printout of the memorandum. It's not that I've got anything I haven't given you. It is available there. You can download it right now as you're sitting here. The wonders of technology. So all the memorandums for all the questions that I've considered are available. Just check where they are and then go back and have a look at it. Okay, so the key issue of an alpha-beta search is, how far away is it? Can't be too far, there we go. Okay, so the key issue here is that the best value that Max has found, or available to Max, when we're considering a certain subtree is alpha, and the best value available to min, the player is trying to minimize the evaluation score of the position, is beta. And we're then going to use that information to try to prune by saying, well, we don't need to consider this tree because we know that one of the players will never allow us to get to this point in the game structure because it's no good for them. So let's go through this and try to see what happens. So the first thing is, if alpha is the best value for the max players, in other words, the players trying to maximize the evaluation score, then starting that value with a minus infinity value makes sense, because anything is bigger than minus infinity. So we're going to gradually track the best value. And same argument, start beta at infinity, because anything is less than infinity, so we will track the best value from min's perspective. The other thing is, the moment alpha is greater than and important or equal to beta, we prune. Because at that point, one of the players is not going to allow us to reach this position because they've got a better option up high. So let's see, hopefully all of that will become clear as we're going. It's a computer algorithm, so it's very boring to apply, but let's go through it just to check that we see how it works. So the numbers written in here are just from yesterday. We're just going to continue from there. So we initialize the values of alpha and beta. Sorry, the values in there, I know they're tiny, are S, V, and alpha and beta. S is the step, in the search. And there I'm mainly looking for what came before what rather than did you get the exact same number as I did. V is the value that this node returns, whichever one it is, and then alpha and beta are obviously the values of alpha and beta. So we initialize the values at the top of the tree. We then don't have anything to select from further, so we go down to the next layer, bringing our values of alpha and beta with us. All right, that's important. Then we've got nothing to select there, so we go down to the next level in the tree, bringing our values of alpha and beta with us. And then we still haven't got any values to select from, so we go down the next level of the tree. Anybody want to guess? Bringing our values of alpha and beta with us. Okay. Then we actually start, because now we've got numbers we can start comparing, and we start doing those. So the first number there, I know you can't see it, is a 2. So 2 is then the best value that this node has seen. It's a min node, so it wants the lowest value available to it. And at this stage, the lowest value available to it is a 2. I've just put a 1 over here to mention this is just to show that this is the first step that I've done. I haven't done anything before this. Because this is a min node, we therefore have to update the value of beta, because beta is the best value available to a min node. And this is a min node, and we've now got a value that's better than infinity. So we update that to give us a value of 2, and our a stays its minus infinity. All right. So at this stage, can we prune? Well, no, because alpha is still considerably less, infinitely less, than beta, so we've got no basis on which to prune. All right, so we then consider the next input, so step 2. We then consider the next input, which is also a 2. Is 2 better than 2? No, it isn't, it's the same. So we just retain our same value of 2 that we had there. Note, I'm not putting the 2 in there, I'm just retaining the value of 2 we had before. We then need to say, do we need to update our value of beta? So is this value better than our current value of beta? No, so we just retain the same value, and alpha just comes along for the ride. Everybody's still happy with this. Now, what I've seen a lot of students do in tests and things the last few years is they then take this 3 and say, oh, well, the node's value is 3. No, it's not. It can't be. It's a min node. The node wants to return the smallest value that it has obtained. So telling me that you've got a 3 as the value of the node doesn't make sense. I know what the people are trying to say is that that's the next one we consider, but that's not what that value is. That value is the value that this node will return when it's finished to the next node up the tree. So is 3 better than 2? No, it's not. So we just keep our 2, keep our minus infinity because we're not at a max node, and keep our 2 because 3 is not better than 2. Everybody happy with that? All right. Yes, sir.
Sorry. Why is there a step 3 and a step 2? Is that not just the first step?
So first step we check that one, second step we check that one, third step we check that one. So it's as we're checking the different ones. And if you don't consider all of them, then you're kind of only considering the first one. All right. So this one is now finished. Now it returns up to the next highest level its value. Nothing else. Alpha and beta do not go up. All right. But the value that the node returns, which is why it's so important that you don't go and put a 3 there, the value that the node returns is then the best value that node had. All right. So we then return the 2 up to level. So this is now going to be step 4. The value of the node is then going to be 2 because it's now got an option that gives it a 2. All right. So its value is now that 2 because 2 is bigger than its previous potential option, which was nothing. If you want to, I guess you could say initialize that as minus infinity and initialize that as infinity. But yeah, let's not do that because I can just see people getting confused. All right, especially under test pressure. Stupid stuff happens under test pressure. So we've now got a value of 2. So now we update beta, right? No. We update beta when we're dealing with a min node because beta is the value that tracks the best value for a min node. So in this case, we update the value of alpha because alpha is tracking the best value available to a max node. All right. So we now go and stick a value here of 2 because 2 is way better than minus infinity. Again, infinitely better. And we just keep our beta. All right. Why didn't we bring this beta up there? Well, because once we're no longer considering this node, this value of beta is no longer relevant. All right, we'll see, well, it'll hopefully become clearer once we start actually getting some cases that are pruned. Unfortunately, with the first few cases, you can't prune anything yet because you're basically just filling up the values of alpha and beta. But anyway, let's carry on. It'll hopefully become clear. So those are now our values over there. Again, is alpha greater than or equal to beta? Hell no. So we carry on with our search. The next stage of our search is to come down here, and again, we bring our values of alpha and beta with us. So we don't initialize with minus infinity over there, we initialize with 2, because that alpha must come down over there, and the beta that comes down is infinity. Okay. So those are what come down to this node. Everybody happy with that? Okay. Then we look at its first value and say, well, this is a min node, so this is then step 5. So this is a min node, and we have a value of 3. Well, that's the best value that this node has seen so far. Remember, we're not considering any other node. The value is just the current node. Does it change alpha? Well, no, it's not a max node. Does it change beta? Yes, because 3 is better than minus infinity from, is better than infinity from a min node perspective. Everybody happy with that? All right, then we say, is alpha greater than or equal to beta? Well, no, clearly not. So we carry on. Then we look at the next one, which is a 2, so it's now 6. At step 6, is 2 better than 3 for a min node? Yes, it is, so we update that. We bring down our alpha because we're dealing with a min node. Is 3 better than 2 on our beta? Yes, it is. So, is alpha greater than or equal to beta? Yes, it is. It's equal. And we now do not need to consider that 2. Okay, so this is a lot of extra effort at this stage to avoid considering one potential outcome. It gets better, I promise. But that's the idea, and we're tracking the alphas and the betas in order to do this pruning. Now, once we have done this, this thing is going to return its value of 2 up until that higher layer. But yeah, just indicate in some way that you've made a pruning here. I see in the memo I just wrote prune there. Just indicate that you have pruned it, that you haven't considered the other one, because what does sometimes happen is people don't finish and they don't complete writing everything. So if you don't clearly say you've pruned it, I can't give you marks for pruning it, unfortunately. So just mention that you have pruned it in some way. So either crossing that out or pruning it or something. All right, if this thing returns a value of 2, so that's 5, 6, 7. Okay, so we then, that is weird. All right, so we then return the value of 2 up here. Is 2 better than 2? No, so we keep our previous one. Is 2 better than 2? No, so we keep our previous one, and our infinity stays over there. Now, we've got a 2 come this way and a 2 come this way. Which one would we return? Which, if it turns out that the best move is coming down into this node, which one do we return? And the answer is the first one. Not every one, not the last one, the first one. So the first time we saw a 2 over there, so if we do come down this way, it's going to go this way, because the first time we saw a 2 was there, and this thing, the first time we saw a 2 was there. Okay, I've had people say, oh, okay, the answer is 2, so it can be any one of all of, no, it's just the one that is returned from the node, right? Also, if we've pruned something down here, why would we now want to go down that route? Because the reason we've pruned it is we know it can only be worse from a max perspective or equivalent to what we've already found. It can't be better. So if we've pruned a node, like we've pruned this one down there, then the solution is not going to go through a pruned node. The whole point of pruning something is that you don't consider it further. It doesn't make sense to prune it and then consider it further, if that makes sense. These are the things I see people do in tests, and I'm trying to explain why it actually is silly and why it wouldn't work that way in practice. Right. Any questions there? Yes?
So, 2 questions.
Yes.
The first one is, how much time would we be expected to be able to do this in a test?
I typically only give 3 questions in a test, with one of a bunch of theory questions, and then one something like this, and one another search, specifically to give enough time. So, yeah.
And if So we prune that last 2 because A is greater than or equal to B.
Yes.
But if that 2 was a 1, we could possibly be pruning a...
No, because let's say that is a 1. So this node then returns a 1 up to that level. What's going to happen to it? It's going to be pruned. So what this alpha coming down here is said that A already has an option of 2, or a max node somewhere has an option of 2. So if we return it anything worse than a 2, we're not going to end up going down this branch because a max node somewhere up in the tree is going to prevent us from getting there. It's actually a great question because it helps to explain why we're doing this. So the fact that this max node, the one I've highlighted here, has an option of a 2 already means that unless we can find something better than 2, which we've now proved we can't, it can only be lower than 2, max node higher up the tree. So while we're working down here, what alpha and beta are essentially saying, higher up the tree, there is a node that is going to prevent us going that way if this condition is present. So that's actually a great question. Thank you for that. All right, so then we're over here. We then return up to the next highest level. This one returns its last value, which is 2. This is a min node again, so we update beta, so that is 2, and our alpha is still minus infinity. All right, we just bring it down. Everybody happy with that? Yes, sir?
Just to clarify, do we return the value in V, not in alpha?
Yes. Alpha and beta are actually tracking what other nodes in the tree can see. And as will probably not become apparent later, but would be nice if it did, is those alpha and beta values will often have nothing to do with any of the nodes within the current branch of the tree that we're considering. They're telling us what happened somewhere else rather than what's happening here. The value, like we saw with the minimax search that was done yesterday, I think, the minimax search means that we're returning the value each stage. So we're still returning values. We're just using alpha and beta to say, okay, we don't have to search any further because we know that one of the nodes somewhere will prevent us from going down this path. Good question again. Thanks very much for all the questions, folks. I do appreciate them. I know I keep saying it, but I really do appreciate them. All right, so this thing now has nothing else to consider, so now we go down a level. And we bring down our values of alpha and beta. So we've now got minus infinity and 2. Remember this one, we just had minus infinity and plus infinity when we came down? Well, now we're coming down with those 2 values. So in this case, we couldn't prune anything because we didn't have, well, in that case, we couldn't prune anything because we didn't have any alpha and beta values. We can now potentially prune here because we already have a beta value over there. So because we're starting to bring things down, we're actually increasing our likelihood of pruning. If that didn't make any sense, don't worry about it. All right. Then we need to figure out what its value is it's getting from a lower node. So we bring those 2 values down, minus infinity and 2 again. Now we have values at the bottom of this tree, so we start considering the values. So we are now on step 9. So we've got a value of 3. Why? Because it's the best value this min node has seen so far. Our alpha we can't change because we're a min node, and our beta 3 is definitely not better than 2. All right, everybody happy with that? All right, and so we continue down. Step 10, we now have a value of 7. Hell no. Minus infinity and 2. Actually, this is an example of what I was saying a moment ago. You can see how the beta and the value there have no correlation. They're related to completely different places. This beta value comes from there, and this 3 comes from there. So we can't return the alpha and beta values up because they're potentially at different points in the tree. But we can return the value up because that's how the minimax search works. Okay, so that's the minus 3, and then 11, we've got a value of 3 again. 3 is not better than 3, minus 2, minus infinity 2. Great, we're done. Yes, sir?
At step 10, why did you write 3 and not 7?
Because it's a min node, and the min node returns the lowest of its options, and 3 is less than 7.
Don't you still just put the 7?
No. That's what I was saying earlier about don't put that in there. Because what happens if this last thing over here was 20, and I now have to return a value up to the next level? I'm not going to return 20. So it's easier just to say, just keep that there. Then you just literally look here and say, okay, the last value is 3, so we return 3 up to the next level, which is what the search would actually do. I know this is very monotonous, very painful. As I say, it's a computer algorithm. Computers are dumb. It's supposed to be simple and repetitive. Otherwise, a computer wouldn't be able to do it. All right. So step 12 up here. This has now had a 3 returned to it, lucky node. So now we have a 3 over here, because 3 is better than minus infinity from that perspective, and our beta is 2. Is A greater than or equal to beta? Yes, it is. So guess what? We prune. So we're not even going to consider that node at all. And now you can start seeing the benefit of this. We're now pruning a significant, well, this is a relatively small tree, but we're pruning quite a big portion of it. All right, whereas we had to go and do all of that when we did the minimax search. So we return that back up to the highest level. In general, you don't actually need to worry about the value you return up here, because the fact that you've pruned means that something up higher probably won't affect it, but just do the effort. Just make sure that you check whether this is better than that. And if it is, just make sure you understand why. Okay, it's a reasonably simple check. Generally, a pruned value will not accept the value of the next node higher up. And if it does, figure out why. Okay, so simple check, hopefully it helps. So we went up to step 12. Yee, these numbers are different. Anyway, now we're at step 13. This returns a 3, so we're still going to keep our 2, minus infinity, and 2. We haven't seen anything better than a 2. Sorry, no, we won't. We'll have a 3 there. Won't we? No, it's a min node. Ha, sorry. It's a min node, so it'll keep the 2. All right. He's slow, but he still gets there in the end. All right. So this then returns up to its next highest node. So that is now step 14. It returns us our value of 2, which is just our last value over there. And our alpha now actually gets updated to 2, because we now have a max node and we've got a value that is greater than minus infinity. Our beta remains infinity. Yay. All right, now to get the next thing that we need to compare, we start going down the tree. So we bring our latest alpha and beta values, make that look like an infinity. Nothing we can do here, so we bring our latest alpha and beta values. Nothing we can do here, so we bring our latest alpha and beta values. All right, so down there we now have that. This is now a min node. Okay, so step number 15, that is there. 15, we have a value of 1, which is the first node over there, so that's 2. That becomes 1. Is alpha greater than or equal to beta? We should have done this in all these tests, but minus infinity is less than any finite numbers. That's why I didn't explicitly say it there. Sorry, I should have. But now this is, in fact, our case. So we now prune over there. And now we've not had to consider any of those, or even that. We've not had to consider that, and now we don't have to consider those two. So you can see we're already starting to benefit. So once we've started building this up, and we've started getting alpha and beta values up here, we actually can start pruning quite a bit. All right, we now return our value of 1 to the next highest level. So this is now step 16. 16, we return our 1. Is 1 better than 2? No, it's not, so it's still 2 and infinity. Boy, do I hope that's right. Yes, it is. Everybody happy with that? All right. We now bring those values down, the alpha and beta values, 2 and infinity again. Step 17, we now have a 6. Is 6 better than 2? Yes, it is. Sorry, 6 better than infinity? Yes, it is. Is alpha bigger than beta? No, it's not. We're still fine. What was that? Okay. Then, step 18, we now consider the next one. It's a 2. So is 6 better than 2 for a min node? Absolutely. So we keep our alpha. Is 6 better than 2? Yes, it is. Alpha equal to beta means we prune. E. So we now return this value up here. Okay, this is an example of where you still need to return this value, and this is now a 2. That gets returned over there. This is a max node, which has a choice between a 1 and a 2. It's going to pick the 2. So it's not always that the next node higher up you don't have to take account when you prune. The weird thing here is that both of these are pruned. That's why we have that situation happening there. Normally, if this one went through and this one is pruned, we then wouldn't have to update the value, but we do here. I hope that makes sense. You always just return the last value you had down here at the end. Yes, sir?
So is it fine if we write the value in the triangle, the value that resulted from that process?
You can, you mean like that?
Yeah.
That's fine, no problem with that. It's already here though. So if that helps you, please do it. That is absolutely okay. There's a reason I mark tests by hand, and that's that hopefully if you do something like that that doesn't affect the result, the computer system doesn't go, oh, you did something you shouldn't have, 0. That's not how it should work. And I understand that is sometimes how it does work. All right, so 17 over there, this is a max node, 2 is not better than infinity, we're still there, life goes on. Yes, sir?
Should it be 19, so step 19?
It should be step 19, thank you very much. See, you're catching my intentional mistakes, well done. All right, so 19, 2, and infinity, thank you. So this one has now finished evaluating its children, so we take it up to the next value. And this is now number 20, it has returned a value of 2. Okay, and then we have the 2 from our previous alpha, and then 2 is better than infinity. Oh wait, alpha is greater than or equal to beta, so now we can prune over here. So we're pruning this entire subtree. We're not going to consider that any further. And now you can start seeing where the efficiency of this thing is coming in, because we're leaving a lot of the tree that we're not considering. And this is quite a small tree. Remember, in a game like chess, you can potentially explore 5 moves, which is 10 plies, into the future. So if you can prune something 1 or 2 layers down, there's a lot less that you need to consider. The benefit that you gain just becomes so much greater. But even here, we can see this happening. We then return this up to the next highest level. So this is now step 21. And yes, this is a 2, but it's not better than that 2, so we just keep what it was. So here, the fact that this is pruning means we're not going to end up going this way. And again, this thing does return a 2, but remember we picked the first time we saw it. And especially here that we've pruned it, we don't want to have this as part of our solution, because what happens if there's something, well, there won't be something significant over there. So again, at this stage, this is our best move. All right, so it's literally the first one we considered so far is the best move for our minimax search. All right, we've now gone up to that level. We haven't changed anything useful. Let's carry on. So now we bring down our 2 infinity. We bring down our 2 infinity. We bring down our 2 infinity. And beyond. Then, yay, I can't believe I thought of that. All right. Okay, so now step 22. The first one this has is a 4, because the 4 is the best thing this min node has seen. The 2 remains the same. 4 is better than infinity. Alpha greater than or equal to beta? No. Next step, 23. Is 9 better than 4? No. And you can already say, well, if we don't even improve the value, we're definitely not going to change alpha or beta. Okay, because ultimately we're comparing, to update these, we're comparing the alpha and beta on the previous one to our current value. So if we don't change the value, we can just actually copy them down. Then step 24, we still have a value of 4 because 8 is also worse than 4. So 2, 4. So we return a level of 4 up to the next level. So it's 4, 2, nope, it's got to be 4, infinity, and that's at step 25. Is alpha greater than or equal to beta? No. Carry on. So that when we bring down our 4 infinity, note this one got 2 infinity because at that stage that was the value of alpha and beta, but since we updated alpha, we have to bring the latest value down. Okay, we're always tracking the latest value. All right, then step 26. Step 26. First thing we see here is a 5. So we've got 4 and 5. Alpha greater than or equal to beta? Nope. So we carry on. The next one is a 9, 27. Is 9 better than 5? No, so we just keep everything the same. The last one is a 5. Is 5 better than 5? No, so we just keep everything the same. Everybody happy with that? Or better, any questions? All right, so we then return our last value up a stage. So that is then step 29. We return a 5. That is indeed better. But it doesn't help us. We don't prune because alpha is not bigger than or equal to beta. So we then return our 5 up to the next level. 30 and 5 and 2 and 5. Is alpha greater than beta? No, it's not. So we carry on. Now we bring it. Now note, for the first time here, we're actually bringing down numbers for both of them. Okay, the only reason for that is you need to go a couple of levels along, sort of sideways along the tree, before both alpha and beta are populated. But okay, so we bring down our 2 and 5, can't do anything yet. We bring down our 2 and 5, and that is then step 31. We then have a 9 over here, because that's the value. Is 9 better than 5? No, it's not, so that just stays 2 and 5. We then have step 32, which is another 9, so our return value remains 9, 2 and 5. And then we return value 33, well, on 33, step 33, we then have a value of 3, which is indeed better, and 2 and 3. It's a slightly philosophical question. Do we need to include those last two, given that there's nothing left to prune? Probably not. Okay, I'm just hesitant to say, yeah, don't worry about including them, because I didn't always do it in the memo. So if you're wondering why that's the case, if in doubt, rather include them. I don't want to go giving you guys rules and then people get them wrong. So it's easier to say always update the alpha and betas, but if you're actually programming it saying, well, there's nothing left to prune, don't worry about updating an alpha and beta actually makes sense. So that's a bit more of a practical type thing. As long as you do stuff that's right, I will give you marks. Don't worry about it. Okay, so 33 has a value of 3, so we return the 3 to the highest level, the higher level, so that's 34 with a value of 3, because that's what we just returned. This then updates to 3 because it's the alpha, and 5 is alpha greater than or equal to beta. No, it's not. So we bring down our 3 and our 5. Then 35. We then have a value of 1. So it's 3 and then 1. Alpha is greater than or equal to beta, so we prune. So we don't have to consider that. We then return our last value, that 1, upper level. So we've got step 35 is a 1, which is not better, so 3, 3, 5. We can then return it all the way up, so we can then go 36. That returns its, sorry?
It's 36 and then 37.
Thank you very much. 36 is still going to give us our 3. Then we go up to here, it's 37. We return our 3, so the min node says that's a 3. You can see why we're returning it up, because that one is now going to be, its best option is now that way. Okay, we then return our 3 up to the highest level on step 38. So is 3 better than 2? Yes, it is. Is 3 better than that? I'm not going to worry writing it in. If in doubt, just always populate those values, but it's not absolutely necessary. So, what is the best move? The best move is there, to there, to there, to, where's the first time we saw 3? To there, to there. So please note, even though our best solution was right here at the end, that did not stop us from rather aggressively pruning the tree at earlier states. So it's not the case that, okay, if you're unlucky and the best move is right at the end, you're not going to prune a lot. So with where the best move is not necessarily going to be the main thing, or it doesn't prevent you from pruning significantly. However, if what often happens is if we have this best move earlier, we're going to prune even more. So I spoke about move ordering the other day and how we can often, in relatively simple ways, using quite simple, just sort of algorithms, figure out ways of saying, well, you know, last move, we found that the best move was down this tree. So we can just start with those two first. We can often prune more, and there are often relatively simple ways that one can achieve that. But we don't have to have the good solution earlier in order to prune. We can just often prune more significantly. Again, the solution is not 3 and 3 and 3 and 3 and 3 and 3 and 3, as many students have started giving me in the last couple of years. It's only the one path that leads to the 3 that our algorithm has returned. What's quite frustrating about that answer that I just gave you now is that 3 has even been pruned. And I've had students say, well, that's one of the possible 3s that you could have returned. So you're only returning one move, and that is this one. Any more questions about that? Yes, sir?
I just want to understand, why is the reason we prune when alpha is greater than beta?
Because it means that somewhere in the tree, there's one of the mins or maxes is not going to let us go down that path. So, where's a nice example? Let's just take this one. So why did we prune over there? Well, the fact that those two are equal means that an alpha has an option of 2. All right? And this is a min node. And we've already got an option of 2. Okay? So in other words, this min node is not going to return anything higher than 2. Because if this path returns a 1, it's going to return a 1. If it returns a 10, this node is still going to return a 2. But we already know that this node at that stage has an option of a 2 over there. So it's not going to consider this. So that's why we prune with these alphas and betas, is because it means that somewhere, normally higher up the tree, one of the nodes is going to make a decision that's not going to let us end up over here. That's the key. So by tracking, hey, we've got an alpha node that has a value of 2, we can say, well, unless this thing returns something bigger than 2, that alpha node is going to present us coming down this path. That's the idea. Another good question. Thanks very much again for all the questions. They really do help. All right. So that's why this works. And it works really well, it works really efficiently, and if memory serves, you actually can't do better than this. So this is again one of those things that numerically you can prove it is the case. So even with the fanciest algorithms, you'll see an alpha beta search probably lurking in there somewhere. However, there are cases in which we try to optimize this, because if we could, for example, have said, well, we know this tree is going to be bad, or the subtree is going to be bad based on goodness knows, we could even more efficiently prune. But we do then start running the risk of pruning things we shouldn't have. And that's where it gets really interesting. Okay. So that's everything about alpha beta pruning. Now, let's carry on with our discussion of the general topic. Let's go for this color. I didn't use it yesterday. So the point here is that we need to make imperfect. We need to make imperfect decisions. Why do we have to make imperfect decisions? Because we haven't got enough time to evaluate the entire solution space. Yes, sir?
So there was a question over here.
Oh, sorry, I didn't see. My apologies.
Sorry, sir. For the alpha beta search, when we're initializing each node, would it be wrong if we come to that as a step when you're saying what alpha and beta is?
I don't care. So if you said that was step 1 instead of step 1 down there. In fact, I think that's what the memorandum does. I don't care. I just want to see the order in which you considered things. So, I've seen many cases where students do not have the same numbers as on the memorandum, and they get all the marks because I can still see that you followed the correct procedure. Again, this is why I mark it by hand, not by a machine that says, oh, you've got a number 2 there instead of a number 3, 0. No, I try to understand what you've done and mark that. So that's why I'm not overly worried that, as I say, my numbers here are actually different. For example, this 25 in the memo is 44. Doesn't matter, as long as I can see your order and I can see your reasoning, that's what I'm marking, that's what I'm interested in. Great, sorry I missed that. All right, so we have to make imperfect decisions because we can't expand everything to its absolute fullest extent. So this is kind of one of the key things. The textbook actually says imperfect real-time decisions, because we have a time limit in which we need to make the decision. So this is a nice example of something where we can't go and just compute the best possible mathematically optimal solution. But we can compute something that is hopefully good enough. And we've reached the point in games like chess and Go where machines can beat the best human players. So isn't that good enough? No, apparently people are still busy trying to make better algorithms. But the point is, from an engineering standpoint, we often don't want to burn hours and hours of computing power to make something 0.0001% better. All right. So we can use heuristic functions to try to say, well, at this point, we should probably stop computing further because we're running out of time, or maybe we should just go one more step for this reason. It does get tricky. So we do have an evaluation function which we need to consider, but the point is we have to stop our search often at a cutoff test and not a goal test. So previously, all our searches ended at a goal test. All right, so we've reached the goal, we've reached the conclusion. In this case, we don't necessarily have a goal test, we have a cutoff test. We either have to cut it off due to time or due to the fact that we're happy with the position or whatever. So that's a very significant difference. We're not searching to find the best solution. We're not even searching to find a goal. We're searching to do as well as we can within the constraints provided. Yes, sir?
So, not with regard to implicit decisions, but with regard to a few of the goal searches that we've done previously. Obviously, in like a real-world application, could you say this is the goal within 5% stop?
Okay, so remember in this case, we're not looking at goals of values. We're looking at goals as states. So then you'd say the perfect solution is this, but any state that comes within 5% of that is then also a goal node. So that's how we would address something like that. But yes, and a lot of these things are great. Here's an algorithm. How do you use it? Again, as I said before, this is a tool you carry around in your little nominal toolbox. Using it is as much a part of the trick as the tool. Slight tangent. So after the test week, we're going to have a bunch of guest lecturers from Saab, Hensoldt, and SANRIN, which is the South African Research Network, the lot that give us the high bandwidth on campus. And what they're going to speak about is the applications of these tools in the environment. So we're looking at the algorithms at this stage. The vast majority of AI in the real world has nothing to do with the algorithms. It has to do with how do you set up the goal states? How do you decide which data to use? How do you decide which data not to use? Which algorithm do you use? But it's very seldom that people actually work on developing new algorithms. I probably shouldn't be saying this because everyone at this stage is like, yeah, this is cool, I'm going to do this stuff, this is awesome. But I had a student a couple of years ago who went into industry and said, yes, we do a lot of AI. And it was literally feed this data into the model and use the model. That was what people describe as AI. So a lot of AI application has nothing to do with the AI algorithm. And yes, I have students that have used classifiers in work and things like that. Basically, it was just pick a reasonable classifier, use it. And it's very, very unusual to see development in the actual algorithms, at least around here. We just don't have the computing power to compete with the folks overseas. It does happen sometimes. But for example, Prof. Maracose from computer science is doing a lot of work on applications of AI. And one of the big points he makes is that AI is becoming a first world versus the rest of the world. Basically at the moment, the US versus the rest of the world contest. And we've got AIs that understand English. Do we have AIs that understand Tswana? Is that fair? Is that something we should be considering? So his group has done a lot of work in trying to address this kind of concern. It's not about developing new algorithms, but it's trying to say, let's build things that are actually useful for people and that address this kind of need. And he's, won prizes at conferences and things. The guy's not doing incredible work, he is. But a lot of that kind of work, a lot of the AI work that we see happening in the world is less about the algorithms and more about how do we intelligently use this thing in order to achieve a goal. And to me, that's the engineering. The engineering is, we've got a tool, how do we get the best value from it? But there's not a lot being done on algorithms, unfortunately. Sadly, there's also a hell of a lot of research that is, new AI algorithm, problem that's never been applied to before, paper. Who cares? Paper. Doesn't mean anything, paper. Sorry. All right, climbs off soapbox. Okay, so big thing here is this cutoff test rather than the goal test. That does matter very significantly in this case. The next thing that is hugely important is the evaluation functions that we use. The evaluation functions that we use. Essentially, where did these numbers come from? So if we've got good numbers down there, we've got a search. That does really well. That prunes things. That is absolutely fantastic. But where on earth did those numbers come from? And what do those numbers mean? And what should we be considering when we try to set those numbers up? So evaluation functions, we want to estimate the expected utility. Okay, so it's an estimate. And I'll say more, when we discuss what this thing must actually be, we'll understand why it's an estimate of the expected utility. And utility is that happiness, goodness, whatever you want to call it. Utility. Yes.
Does that mean we just need a heuristic?
Yes. But, next line in the notes has a very strong effect on the performance of the algorithm. So if you have a better estimate of the performance of the algorithm, the better estimate of the utility of a given position, you will get a better algorithm. All right. And this is, given that alpha beta search is pretty much the thing to use, this is where you can really make a difference. Okay. What do we mean by this estimate of the expected utility? What does it have to mean in order to be useful? And the point here is that we want to order must be the same, or must be, what do the orders do? What? Oh, that's right. The order must be the same as the true utility function. Yeah. Sheesh. So this is what we're looking for. And what we mean by this is, if the true utility says, this position is better than this position, then we want this thing, this estimate, to have the same ordering. Does it matter whether the one is 10 million and the other one's 1 million? Or the one's 3 and the other one's 2.9? It's the order that matters, because fundamentally, remember, the alpha beta search is looking at the which one is better, not how much is it better. That doesn't feature. So it's this ordering that really matters. And when we get this ordering wrong, that's when the algorithm starts performing badly. Okay. Very important point here. Speed kills. No, speed matters. All right. Because a lot of the time, the performance of an algorithm is, or the performance of a game playing system, is its ability to see further into the future. So the ability to see further in the future is often better than the ability to have an absolutely perfect estimate. It's obviously a trade-off, because if you have something that gives you the wrong order, like very comprehensive, I don't care how quick it is, so give me a random utility, just use a random number generator. That's clearly not going to work. It's going to be really quick, but it's clearly not going to give good results. So there's obviously a trade-off between those. So, what is it that really sets an evaluation function apart? And let's put this in another color, because it's this important. So, it must correlate. What? It is another color. It's that important. I need to highlight it. All right. So, we need to correlate with the probability of winning. So when we're speaking about our utility function here is, we want to know from this state, what is the probability of max winning and what is the probability of min winning. The greater the chance of max winning, the higher the value. The greater the chance of min winning, the lower the value. Or in multiplayer, the greater the chance of the relevant player winning. Okay. I wanted to say something now. Oh no! Oh, this is why we have to use an estimate. Remember, we can't expand every game and every move from every possible position to the end of the game. That's kind of the whole point of what we're looking at here, is we can't do that. That's why we have to use an estimate rather than the actual value, because there is no way to determine the true utility from most game positions, because the search is just too far for the number of atoms in the universe. So in that case, we have to make an estimate of what the probability of this positioning leading to a win is, even though we're not guaranteed that it will be the same. But as long as our order is good, so this position has a better chance of winning, so let's say in some way we're able to determine that, and it has a higher value than this one. The order is correct. As long as that's the case, we're good. So what we actually want to determine is this probability of victory from this position. So in other words, if we take every single possible move, what is the probability that I'm going to win from that game? Or if we can go and do the alpha beta search for that all the way to conclusion of the game, in other words, we're not in this situation, we actually end up with a goal test. That's what we actually want. Am I guaranteed to win? Or am I guaranteed to lose? Or do I have a 50% chance of winning? If we can't compute that, we need some sort of an estimate. And that is what makes this challenging, and that's actually what makes games interesting for humans. Again, because yes, I'm stopping now. Is because in thousands of years, we haven't solved chess. We can't say what the absolute best possible first move in chess is, because we can't solve it to conclusion, so we can't get the true utility, so we use an estimate based on Friday. See you then.